so here's example 8.5, and we're going to apply the work kinetic energy theorem that we just derived a few minutes ago. That is the idea that the work net work is 1/2 mv final squared minus 1/2 mv initial squared, which is really final kinetic energy minus initial kinetic energy, which really means it's simply the change in kinetic energy. That's how much work is done as this object changes its kinetic energy states. So example 8.5 right here, we have a large or maybe not large, but it's a 4.10 kilogram box of books. So I'm going to draw this right here. Here's my box of books, 4.1. You know, I'm going to draw that in black because that wasn't a very good rectangle. Anyway, here we go. Ugh, getting worse. I know why this is. It's because my pen tablet is at an angle and it's not straight up and down with. There we go. That should be better. Okay, that's our box of books, and the mass is 4.10 kilograms. Okay, which means that our, I still can't draw a straight line down. mg, we take that times 9.81, that would be 40.2. 40.2 newtons. That's our weight force due to this mass of books. Okay, well, it's lifted through a some distance, that d right here. So it's lifted up to some height. I'll draw this as a dotted line right here. That's the height it's lifted to, and that height is what is it? 1.6 meters, right? 1.60 meters. Okay, we're lifted vertically from rest. This is important. From rest. What does that mean? That means the initial velocity right here, VI, equals 0 meters per second. And what's causing it to lift up? We have a force that somebody applies to it, an upward force. That's this right here, 52.7 newtons. All right, so I'm gonna. Man, I've been away from this pen tablet for too long. All right, we'll call this force of person. How's that? Force caused by the person equals 52.7 newtons. Okay, so that person is applying this force, displacing it through this distance right here, 1.6 meters. Starts at rest, and there's also gravity, of course, acting against that person as well. So what are we trying to find here? We want to find the work done by the person. Okay, the work done by gravity. How much work is done by gravity? And by the way, if this object is actually going from here up and gravity is acting downwards, what kind of work can we say gravity is creating? But negative work, right? So we'll find that. And we want to find the final speed of the box when it has been moved to that displacement right there. Okay, so let's start with our work done by the person. Okay, I'm just going to call this W person. Very, very, very original. And that would be the force of the person, F person, times D, right? Moving through that displacement or that distance D, times a cosine of phi, the cosine of the angle between that force and the displacement. But look, if it's being displaced this direction, right here, and here's our force that's being acted in that very direction. What's the angle of phi between that and that? There is no angle. They're basically going the same way. So the angle is, what is an angle? But it's 0. Cosine of 0. So I'm going to actually strike that out and say the cosine of theta, or the cosine of 0, what is the cosine of 0? It equals 1. So that's usually when we strike it out, something cancels and goes away. I'm going to just say, hey, look, that becomes 1. Okay, so what does that all equal? What's the force of the person? That's 52.7 newtons times the displacement, which is 1.60 meters. If you really feel like it, times 1, right? Because that's our cosine of theta, or cosine of 0 degrees. So that, multiplied all together, gives us a work done by the person of 84.3 joules. 84.3 joules. Great. That's the first part of our answer right there. What's the work? Time machine could not. I don't care about that. All right. Work done by, and I'm going to, instead of writing gravity, I'm just going to write by mg. Work done by gravity. What is that? Well, that would be the mg gravity weight force that we've been referring to. That's the force right there of 40.2 newtons times our displacement, right? Times a cosine of phi. Okay, well, think about this for a minute. If this angle right here between our force and our person force and our displacement is 0, what is the angle between this direction force, this weight force, and the displacement? Oh, that's 180 degrees from the direction of displacement. And so the cosine of 180 is going to be -1. Right? The cosine, I'll write down below here, cosine of 180 is -1, whereas up here, cosine of 0 equals 1. And that means that this guy right here is going to become -1. Okay, because that angle is 180 degrees off of the actual direction of motion. So let's write this out. So what's the weight force? That's 40.2 newtons, right? 40.2 newtons of weight times 1.6 meters times the angle that it differs from the actual displacement. Well, it differs by a whole 180 degrees, so it's going to be times -1 that we multiply our weight weight force times displacement to get our weight work. So that means that our work done by weight, or work done by gravity, is going to be 40.2 times 1.60 times -1. That should be -64.3 joules. -64.3 joules. So what's the net work done on the box right here? Well, that should be easy. That's simply 84.3 joules minus 64.3 joules. That gives us a total of 20.0 joules of work, which is really the net work done by the person on this box to move it upwards. Okay. Great, we have a net work of 20 joules done on this box. The last part of the question asks us, what is the final speed of the box? Final speed of it. Well, we just did a problem, or we just derived an equation where we relate work to mass and speed, and that was a couple slides ago. That was our kinetic energy theorem. So that means that the net work is going to be equal to the change, it's a bad delta, the change in kinetic energy. Or really, 1/2 mv final squared minus 1/2 mv initial squared, right? So, okay, we've got velocity in there, and we should be able to solve for velocity. And hey, check it out. This right here, that becomes 0. Why? Because our initial velocity, oops, drew that to the wrong spot. Our initial velocity is 0, so it makes that whole part 0. So really, we can say that our net work, I'll write down here at the bottom, equals 1/2 mv final squared. Okay, so let's solve for our velocity final because we know everything else, and we simply just plug and chug. So let's take our 2, bring it across the equal sign, and bring it to the top. So 2 times the net work divided by, let's take our m and drop it down below, equals v squared. And so v should equal the square root of all that. 2 times the net work divided by m. I'm running out of space here, but so it's the square root of 2 times, what's our net work? 20.0 joules divided by our mass. What is our mass? All the way back at the beginning here, 4.10 kilograms. 4.10 kilograms. And we simply plug and chug. What do we get? 3.12 meters per second. Meters per second. And that, my friends, is our final velocity. Made easier by the fact that our initial velocity was 0 meters per second. But even if the initial velocity wasn't 0, it would just be one more little expression we'd have to calculate out, but it would be just as easy to find. So that's our example 8.5, and I think for the sake of time, I am going to wrap this one up, and I'll catch you on example 8.6 on the next video. See you then.